It's okay, I think we're ready to go. So you can still hear me, I believe, right? Yes, okay, cool. So this is where we stopped last time. So remember, essentially, what we're doing in the last lecture, we were trying to understand the interface of a which is provided by the operating system kernel, right? So its interface is provided through system calls, and we looked at a couple of them. We know how we can open file descriptors. We know that we can read them and write them. And we learned two important system calls which allow us to create new processes, fork and exec, right? Fork just duplicates the existing process, essentially clones the address space, and it's almost identical. It just returns a different return codes in the parent and in the child. So in the parent, it returns the parent ID. In the child, it returns 0. And exec allows you to reload the address space of a process with a new binary. So essentially, when you're running in some hello world main and you do exec WC, for example, you will switch and start executing WC from WC's main, right? And hopefully this is clear, right? And the real thing on which we got stuck, okay, hold on. So what are we doing here? We need to accept this. The real thing is to understand why this weird combination of fork and exec makes sense, right? And I was trying to convince you that it makes sense because we can build this IO redirection. And specifically, we can build pipelines, or we can pipe input of one program of cat into something what is called a pipe, right? So output of cat is piped into an output of cat is file descriptor 1, and our input of grep is, file descriptor 0. And again, output of grep goes into a pipe. This is a pipe, and this is a pipe as well. And the input from this pipe goes into WC, right? Standard descriptor 0. This is standard descriptor 1. And this allows you to combine multiple programs into something more meaningful. You can query data, you can really do something useful. And everything is, remember, is built around the shell, because back then it was the interface to the machine, right? Okay, so we looked at this example where we said, okay, we're trying to understand how to build this pipeline, right? And what happens here is, imagine how to just, imagine it's a shell which recognizes that you have to implement a pipe, right? And what we do here, the shell itself first forks. Inside the parent, it gets 32 parent ID of a child. Inside the child, it gets 0. The file descriptors, remember, this is important, that the fork copies the file descriptor of a parent into the child, right? So it's identical file descriptors. If parent had file descriptor 3 pointing to a file, child will also have file descriptor 3 pointing to a child, right? And there was this important convention that if you close the file descriptor, there will be a hole in your file descriptor table. So for example, you had some file descriptors opened already, right? And you close this one, your file descriptor table will have an opening now, right? So this one will be empty. Those guys will be all taken, right? But this one will be empty. And the next open file descriptor will have the lowest number, meaning that if you do open now, and you close, for example, 0, 1, 2, 3, right? If you close 3, now if you open a file, and you can't really explicitly specify the file descriptor, but the file descriptor value, which will be returned by the operating system, will be the one with the lowest empty unoccupied number, right, in the file descriptor table. So it will be 3 in this example, right? Okay, so, and this is essentially what shell can do with the child. So essentially, an end goal in this specific example, when you're redirecting input of cat to ls.c, what the shell will do, it will fork. The file descriptors will be identical. So file descriptor 0 will be connected to the terminal, right, in both parent and the child. Sorry. Hold on here. So it would be like that. But after you close 0, it will become empty, obviously, right? And this is why when you open ls.c, the operating system chooses the lowest unoccupied number, and you have the file descriptor 0 will be pointing to ls.c. And remember that file descriptor 0 is a standard input. Now, if you do exec here into cat, right? Then the cat, which will start reading from the standard input from file descriptor 0, will not be reading anymore from a console, but will be reading from ls.c, right? And this is a beauty of Unix, right? That it allows different objects to hide behind file descriptors, right? So in this example, this is a device, right? And in this example, this is a file, right? So, but since they provide identical interface, kind of like an interface in an object-oriented language, right? So they have read and write methods. You can open and close, right? So is this clear? Did you understand how this example was IO redirection? Are there any questions? No questions, or maybe someone is typing, we'll catch them later. Okay, so the whole point is that exec replaces memory of the process, but leaves its file descriptor table untouched, right? So whatever shell sets up for this child, after it execute exec, it stays intact, right? So that's why the child will be executing on this file descriptor table. And this combination of fork and exec, right? It allows the shell, which essentially forked, and this one is to be it will turn into cat, but there is still a window of time between fork returns and exec, which it executes here, right, into cat. This window of time, it can do anything with the file descriptor table of a child, right? And so this is the power of these two system calls. So you first fork, then you mess up with the file descriptors of a child, implementing IO redirection, right? And then you exec. That's why this, like, it's one reason for why this couple of system calls was invented, and it's quite powerful. I mean, it lives for over 50 years, because early Unixes, remember this picture of Ricci and Thompson, right? So who were programming this PDP-11, Unix was created in 1970s, right? So it's already 50 years old. Okay, here's a more concrete example. This is how it looks in the code, right? If I show you a couple of diagrams now, again, same example, we're implementing IO redirection for cat. So what we're doing here, we're just simply forking, and inside the child, we're closing file descriptor 0 and immediately opening ls.c and then execing into a cat, right? Which means that this program, which was running here, will turn into a cat, and we'll be reading from file descriptor from its standard input, and we'll eventually we'll be reading from this file ls.c, right? Okay, and this is again the same explanation why fork, not just exec. Why? Because imagine you say, okay, I don't want this weird couple of system calls. Maybe I will be just like on Windows, something like create process, right? The thing is that imagine all this multitude of configurations which you have to be able to support to say, look, I would like to replace this file descriptor with that, and I would like to do this and that with the file descriptor table or with the state of the process, right? So arguably, you probably can't support, but it gets a little bit ugly and inflexible. And to be honest, I can't say that fork and exec is an ultimate, couple, and it's flawless, right? So because it's kind of ugly is that first you do a fork, and eventually you do a shell here, and you do another copy of a shell you created, right? You waste your time in the operating system and resources creating this shell, flip a couple of file descriptors because you literally execute 5 lines of code, and eventually throw it away almost instantly because you do exec, right? And this address space turns into something like WC or cat, right? So it's not ideal, especially imagine you want to create a lot of small processes instantly. And maybe, the something like create process is a better deal in this case, because you can always optimize this fork with copy and write, and all mature operating systems do that. But again, there are pros and cons, and there are good papers about criticizing fork, but at the same time, this combination was proven to be successful, and so let it be for now. Maybe it will die eventually, but it's there. And again, if not redirecting file IO. Imagine you're just writing GUI applications and you say, look, I don't care about this standard input and output. Like there is no standard input. I'm talking like to the window manager. I'm opening some files on the web. I don't care about it. Then this idea should die. So like it shouldn't be your central mechanism in your operating system design. Just make something else, like create process. And that probably was the logic behind Windows. They said, okay, we're not going to support shell. And you can argue whether it was a smart design decision back then, because they're kind of coming back to supporting shell now, right? Because it's so ergonomic in so many things, right? That supporting the full tool chain of Unix or GNU utilities, right? Like all this WC and everything, right? Makes sense. So Windows probably will try to support it, or they are moving towards this direction, right? But for graphical user interfaces, fork doesn't make sense, in my opinion. How would the system go back to standard out? Would the user need to set it back to console? Let me quickly explain. That's a great question, actually. Look, this is what shell is doing. So shell is running, right? It shows you a command prompt. Oh, sorry, wrong, this way. And you type something like cat input ls, right, .c. And at this point, what shell will do, it will fork a child, like we just did an example, right? In this example, there will be second shell. This shell will do the IO redirection. So standard input, for example, will like, or maybe let's redirect both standard input and standard output to foobar, for example, right? So it will redirect 0 to ls.c, and it will redirect 1 to foobar for this invocation, right? And then it will do exec, and then this process will turn into cat, right? So there will be cat running at this point. And this guy will be waiting on it. So it will wait for it to finish. So maybe you like, for example, in this example, we still did not redirect standard error, right? And maybe something goes wrong and some error shows up on the screen here, blah, blah, blah. But since you're waiting, at some point, this process exits, right? And at this point, shell knows, okay, the child has exited. I am okay to print out the new command prompt on the screen, right? So when this guy has died, it's like when it exited. So it's per process. Remember, its file descriptor table will be cleaned up by the operating system, and we will take a look at how it's done. And it will close all the file descriptors, close all the files. Like in this example, it will be ls.c will be closed, foobar will be closed, but nothing happened to the file descriptor of this shell. It can still print on the standard terminal, right? And it will continue printing, right? So nothing like really happened to this process. It just survived all of it, right? It continued running. And imagine you type something like just WC with no, on some file, I don't know, like, or even on input of cat.c, for example, right? In this point, this WC will output something on a screen like 16 lines, 75 words, and 635 characters, for example. And again, it will do the same. Let me change the color here again to blue. It will create another fork of a shell, will do IO redirection, will start exec into WC, which will be reading from cat.c. This WC will output something on a screen, but the shell will be still waiting for this child, right? That's the logic of the shell. That's what it will be doing. And when the child will exit, okay, its file descriptors will be cleaned up by the operating system, and the shell can again output the command prompt, knowing that no one will override it, because at this point, shell is the only writer, right? And you can say, look, no, you can actually break this guarantee. So you can create zombies. So kind of this guy can fork, create another child. And I forgot exactly what this, if you were waiting on this one, I think you will exit. And if this one still prints out to the standard output, I think it will overwrite. But I'm not 100% sure. We can like take a look at the implementation, to be honest. But you can see that more or less normally it makes sense, but like you can probably run into corner cases. Do we need to always run close before running open? Exact, like shown in the cat C example. Yes, because look, the point is that if you don't run close, if you don't do close, right, your standard input, for example, is connected to console. And your standard output is connected to the console, right? And the standard error is connected to the console. This is 0, this is 1, this is 2, right? So this is in, this is out, and this is error. Sorry, just clicked something accidentally, error. And imagine you don't do close. Then when you do open cat, it will open 3, right? This will be pointing to cat, right? cat.c, like in this example, in which WC, its input gets redirected to cat, right? So, but if you do close 0, and then do open, then this file descriptor will be allocated because it's the first empty file descriptor in the file descriptor table, and then it will be pointing to cat. Clean? Got it? Maybe you can try F reopen. Yes, so those system calls were added later. And I think there is so exactly. So now there is a way. So, but back then there was a convention, and it's a little easier to understand, I think, the intent by looking at the small convention. Now there are some additional system calls which allow you to like close a specific file descriptor and then open a specific file descriptor if it's unoccupied, right? So yeah, but it's kind of the same principle. Is there any circumstance where a process can share the same file descriptor table? No, there is no. There is only a case when multiple threads of a process. Oh, no, hold on, like even threads, you would probably create individual file descriptor tables just to make it sane. No, so I don't think any operating system will allow two processes to share a file descriptor table. Why is that? Just kind of like, think of an object. Yeah, I don't know how to explain it. I think you can run into weird cases where, like technically speaking, you can make it work. It's probably, there is no real use case which justifies this sharing. Let's put it this way. That's my view.
Was this one of the quiz questions?
Can you say this again? I missed them, sorry.
Was this like what one of the quiz questions was it like used?
One of the which questions?
I think there was like an example of like some code that closed a file descriptor and then like used printf or something like that.
Yeah, but hold on, like what are you like? Maybe you're connecting to something I said and I'm missing this connection.
Oh, it's just the file descriptor, right? Like the closing one, and then it like changes what it points at.
Yeah.
Yeah.
So you're saying that will be a weird behavior if another process will close it and I will open. Yeah, that's a good example, meaning that unless those two processes will communicate somehow that, I'm closing and I'm opening, right, you will immediately run into some troubles, into some kind of a race condition in which the file descriptor gets closed underneath or something like that. But why can't we use FD3 instead of FD0? Okay, hold on. This is the whole point. The cat, the whole logic of cat. Let's just quickly go here. So let me show you the cat. So if we switch to the source code, if I show you the source code of cat.c in x86 operating system, what it does is it will try to always read, like, look, it will check, okay, if there are no arguments passed to me, I will be using 0 as my input because I know that the 0 is my default standard input, right? And what it allows you to do, it allows you to program programs which says, okay, by default, we always will be using 0, but this 0 can point to something else because of the IO redirection, right? This is kind of like, you don't have to change your program to implement IO redirection. The shell will do it for you, right? And that's the beauty. It's kind of like, that enables composability essentially, because you say, I have this black box, it will do something, but will always print something on the standard output, right? And we'll read from standard input. Imagine view it as a function, and now you can connect this function to something else, like to output of another program, without changing this function, without changing this black box, right? That's the whole kind of design motivation for this design choice. Good. And if you say, look, I want to I want to use FD3, file descriptor 3, then you have to somehow communicate that FD3 is really your input. So you have to pass this argument. So you can, instead of doing something like cat redirection, I don't know, cat.c, right? You will have to do something like cat, my input is 3, for example, right? So which is a little bit uglier than just simply this, right? Although you can say that all programs by default have to support -i, like take an input, right? Okay, so let's keep going, otherwise we'll never finish this. So, okay, now we understand how to use a pipe to connect to programs, right? So create a pipe, fork, attach one end to the standard output, attach another end to the standard input, right? So I hope that at this point, it's clear. If a parent opens the file, then forks the child. If the child begins to read from the file, does it move the file offset for the parent also? No, only for the child. That's the whole point, right? So you fork and then they run independently. It's the same file, but the file offset's now independent. Actually, hold on. I said this and I'm not entirely sure anymore. Let's keep this question. That's a great question. And I somehow blinking on the answer, but it will become clear. It's very easy to read from the source code of x86. So how about you wait until we get to the file systems and you can ask the same question then again. And then we will really look at the concrete implementation and we'll make a conclusion. This is how it works, right? If a parent opens the file, then forks the child. Yeah, that's what's the question. Okay, cool. Let's postpone it. I can answer offline, but if you're curious, I can answer on Piazza. It's easy to read quickly, but I don't want to lie to you right away, although not sure right now. Okay, another example here. So this is how we create a pipe, right? So essentially, some program, you create a pipe. Pipe itself takes an array of 2 integers, right? A pointer to the array, which means that those integers, like one will be an input end of the file and it will return a number like, for example, 3 and for example, 4 here, right? So what happens, we essentially this array will be populated with with 2 file descriptors, one pointing to the read end of the pipe and one pointing to the write end of the pipe, right? We fork, right, inside the child. So we close standard input, right? We duplicate the read end of the pipe, right? So this is the read end of the pipe, and this is the write end of the pipe, right? So what happened is this is inside the child. 0 was pointing to somewhere. And remember, we got 3 and 4 as pointers to the pipe. So imagine this is your pipe, right? And this is the read end, and this is the write end of the pipe. So from the read, you can read, from a write into write, you can write, right? And here you close 0, right? So this one disappears. And you're doing another system call, which is duplicates a file descriptor. So you say, I will duplicate P0, which is 3, right? Which means that again, it will the lowest unoccupied file descriptor will be chosen from the file descriptor table. And this connection will be established, meaning that standard input is now connected to the read end of the pipe. You now close P0 and P1. So those 2 lines disappear, right? And you exec into WC, right? So WC will be WC is running now, and inside WC, 0 standard input is connected to a pipe, right? And it is waiting for the input. Inside the parent, what you're doing here, you say, I'm going to be writing hello world into this pipe, right? So you say, look, I had read and write ends of the pipe. I will write hello world just straight into the right end of the pipe, right? So this hello world itself will be written in this pipe. And at this point, WC can read the characters. It will read hello and world, right? However, it's critical to make sure that you close both reads and writes ends of the pipe in the parent in order for the WC to exit. Because if you don't close them, right? I mean, when the process will close, the file descriptor, the operating system will clean it up. But if you're doing something dynamic and this process is not closing, you really, if you want to really communicate with them, you have to close them, right? To make sure that at some point WC detects, okay, there is nothing else to read from a pipe, and I will be just like, I will exit myself, right? But that's an example. This is kind of like, why is it important? Because I will ask you to implement your own shell, and this logic, but more general, you will have to build, right? So you have to understand the basics to understand them, to build more general concepts, right? So the second homework will be building a shell. So the first one, which we'll probably release today, will be about writing just simple Unix programs, like very, very simple stuff. Just make files and how to use GDB and stuff like that. But the second one will be building a shell. So pay attention here. Okay, so it's exactly the same figure which I did, right? Same illustration. So exec WC. If WC itself starts reading from 0, it's connected to the read end of the pipe, right? And here in the parent, we're using P1, which was, in our example, it was 3 and 4. So really this one has to be 4 because this is the right end of the pipe, right? And we say hello world into this pipe. Hello world here, right? Okay, cool. Hopefully this is clean. And similarly, we can construct this pipeline, right? So essentially just shell will fork, we'll do IO redirection, we'll exec into a cat, right? This was shell. And this shell, which was running the parent shell, will do this. This will create a pipe, right? So, which means that this cat will be connected to the pipe. And then we'll fork again, right? This guy will have a shell, and this one will connect to this read end of the pipe. So this is the right end, this is the read end, and then exec into grep. And of course, grep will stay connected to the same pipe. And then this shell should also be before execing into a grep, it should fork itself as well into, like, it should first create a pipe, right? And then fork into another shell. So this shell will inherit the file descriptor pointing to like P1, and this one will be pointing to P2. And this one will exec into WC, right? And WC will stay connected to the same. This is P1, this is P2, right? And this is how time goes, kind of, right? So you kind of see that I got it. I can understand how I can, if I have a recursion and I have to build a pipeline with multiple pipe symbols, I understand that, okay, I will be forking recursively and doing higher redirection and execing, right? Okay, that will be in the homework. So, okay, cool. So right now we have the following powerful conclusion. This combination of fork and exec allows you this flexibility, right? So you can do this recursion because you fork in a shell and you fork again, right? Because this is the logic of your code. You say, look, I got it. I want to actually create recursively pipes, right? And this will be hard to encode with this create process, right? Saying that, like, imagine what kind of, I don't even see how to do that, but maybe it's possible. You can come up with a solution, I'm pretty sure, which says, okay, look, I will be like, the end goal is to construct a pipeline of like 10 symbols, right? Or 10 pipes or something like that, right? That's a little tricky, but probably doable. And this fork and exec essentially form the core of the Unix interface. So those functions, of course, along with read open and stuff, they're the most interesting. They created the whole ecosystem which lived for 50 years and is still successful. So again, people are still widely using shell. It's for certain tasks, it's still extremely ergonomic, right? For certain other tasks, it's not as good. So it depends on what you're doing, right? Okay, so we're done with fork and exec, but we have to look at a couple of other system calls, right? Because some of them we actually mentioned. So exit allows the process to terminate itself, right? So it's essentially stop running, right? And the operating system cleans up all the resources. Wait allows the parent to wait for a child, right? And that's like mainly like in case of a shell, when the child is printing, parent is waiting. When the child exits, the parent knows, okay, same child will not fork, will not be doing anything crazy, or will wait for its own children, right, to stop. And at this point, it's safe to print out the command prompt again. So it's not going to be overridden here by the child because it's already done, right? There is system call which allows you to create a directory in the file system, right? Open can create a new file. We've seen it. Make node allows you to create an empty file which is labeled as a device, and the operating system will be handling it as a device. Console is one example of such device in x86. fstat allows you to retrieve information about the file. Link allows you to create a symbolic link to a file, meaning the file itself is a data structure in memory of the operating system, and it corresponds to another data structure. They typically, like, there will be a file, there will be an inode, right? And this is where, if you want to have two different offsets into a file, so you can open the file twice, meaning that, both files which will have an offset, right, will point to the same inode. And the inode corresponds to like actual data structures on disk, which keep the content of the file, right? But I think the file descriptor table of a parent and a child will, I don't know when, that's essentially when you do a fork when you do a fork, the question is like, do you copy this and create a new file object, or you rather just simply copying a file descriptor? And if you do, then you're sharing the offset. And if you don't, then offsets are different. That's the answer to the question which was asked before, but I don't really know whether the operating system does it, but it's very easy to locate. And we will go through the fork. No, hold on, we will go through the exact system call later in the lectures, but actual implementation of exact, but maybe it will take us a month to get there, right? But what I meant to say, this link allows you to create a symbolic name, some kind of like foobar, one name, and maybe somewhere like bin, I don't know, bin bar will be just another name, which will essentially lead you to the same inode, right? And that's allows you to give one file multiple names and put them in different places in the file system, right? And unlink allows you to delete a file. So for example, to create a temporary file, you can simply do open, like create the new file, write permissions. You will get a file descriptor, which you can read and write, and you immediately unlink it, meaning that you say, okay, there was no place in a file system which refers to this inode, right? And the file system will garbage collect it, but for as long as the program is running, or until you do the close FD, that FD still exists in a file system. It doesn't have a name, so it's guaranteed that it will disappear later, right? But it's like for as long as you're running, or as long as you close this file descriptor, that's your temporary file. Okay, and remember I said, okay, it's very beautiful. Think about this x86 operating system kernel and Unix in general, right? Because early on, in all the system calls were able to fit on one screen, right? So we looked at fork, we know exit, we know wait. There is explicit kill, which allows you to kill a process. That's what I do before the lecture starts, right? Because I have a lot of firefox running. Get pid allows you to get the process ID of the current process. Sleep allows you to sleep for n clock ticks. So essentially just say, look, it's kind of like allows you to wait for a specific amount of time if you know the clock tick, right? Exec, we talked. SBRK allows you to grow the memory of a process by a number of bytes. And if it's a negative, then you shrink. So this is how you allocate and release memory inside the process. And on top of SBRK, you can build malloc, which allows you to, SBRK just allocates chunk of bytes. And if you want fine-grained objects on top of it, you have a malloc library, which says, okay, now I will manage this memory. And if you say alloc 32 bytes, I will alloc a small object of 32 bytes. If you say alloc 127 bytes, I will alloc a slightly larger object of 128 bytes. And then, okay, like give it to you, right? Open, read, write, of course, we looked at this. Close, dupe, duplicates file descriptor. Pipe creates a pipe. Change directory changes the current directory of a process, right? Because unless you start your lookup with a slash, which starts with a root, right? If you do something like foo, open foo, then you will start from a current directory, right? And each process will have a pointer to the current directory, right? It's just, we will get to file systems and how the naming layer works, and you will understand it better. mkdir create a directory, mknode create a node device, file stat, link, and unlink, right? Fits on the screen. I kind of argue that almost anything what you want around, I mean, GUI will not work, obviously, right? You might like abstract GUI behind the file descriptor, saying that the GUI is the file descriptor 55, for example, and then you can like keep writing bytes there. It doesn't work that well, but you can share. There is no shared memory primitives in this kernel, right? So essentially, one process cannot share memory with another. Otherwise, you would be able to kind of like share frame buffers, and that would help you to implement GUI much better, right? In this, the only inter-process communication mechanism is a pipe, right? So essentially, two processes can share a pipe, and one can read and one can write. But still, reasonably powerful. You will be impressed. Like, you know, remember, I forgot if I was telling you this story. Like, imagine you want to do a tiny startup, kind of like running a Fitbit device on your wrist, right? Maybe it takes blood pressure measurements. You say, I don't really know how to build a operating system. I don't really know what I need, right? But if you say, okay, I will take x86, just port it to run on this piece of hardware, it will take you a long way, right? So this is amazing. So you'll understand how far you can go with this system call set. Okay, and what I also wanted to say is that in many ways, x86 is a file system, is an operating system which you're still running today, right? So x86, so Unix version 6, right, was somewhere here. And here we have Unix version 10.5, I guess, from Bell Labs. Like, same guys, Ken Thompson, Dennis Ritchie, and everyone else. And from there, like a couple of systems got forked, right? So for example, Andrew Tannenbaum did this not exactly a fork, but took inspiration, I guess, and created Minix, right? And wrote his operating system book. And then he created Minix 3, which is a microkernel, which is a different kind of a beast, but still. And from that Minix, you know, Linus Torvalds also took inspiration from both Minix and from the GNU system, which was created by Richard Stallman, and created Linux, right? And that's Linux is still alive and going strong, right? So here, for example, a free version of Unix, a BSD free, like Berkeley software distribution, and then free BSD, right, got forked. And there is a connection because this BSD kernel, and even I would say it should be like drawn actually like this, because actually macOS took large parts of FreeBSD kernel and executed them on top of a different microkernel, which is called Mac, right? And this is your macOS kernel, right? So it's Mac microkernel plus FreeBSD, and like their open source kernel is called Darwin. So you can take a look. Kernel is called XNU, I think. And I think, yeah, they updated, so you can get one of the most recent versions of their macOS kernel as an open source, right? Darwin is an open version. So yeah, so there was a huge influence on how everything was created. So Windows is not in the charts. It didn't took inspiration from Unixes, right? So it's a little bit, they did it from scratch, like first like torturing DOS operating system, and then like building their NT microkernel or NT kernel. I mean, it's nice that they did it differently, but I don't like it that much. It's less ergonomic to me, I guess. Microkernels versus monolithic kernels, famous Linus versus Andrew Tannenbaum debate, right? Exactly. Do you know what happened to system, what is it, system 4, or does nobody know? I have no idea, but I'm willing. I'm not a historian, to be honest. I don't know that many anecdotes. But again, so this lecture is over, right? So this is good, and it's time for us to start a new one. And the new one will be about x86 assembly. Which is on its own is a lot of fun. So let's quickly switch here, go into lecture 3 and start it. Okay, what's the reason to talk about x86 assembly, right? The reason, besides that it's a lot of fun and it's like a lot of interesting education experience, I think it will enable you to do stuff which you were thinking was impossible before, right? Because first of all, I'm saying that understanding x86 assembly is not that hard. Writing large programs and writing correct programs is hard, especially from the first time, but then you can get them right with debugging, right? So that's my point. Essentially, you don't have to do a PhD to understand x86 instruction set, and you don't have to sit for years to and like reverse engineering programs just to understand it, right? And later in our class, we will be looking into what's inside the process, and we will take a very in-depth look, right? Essentially, I will show, I will introduce which sections are generated by the compiler, how they get linked together. We will look at the examples of real programs, right? And I will convince you that, okay, the stuff which I type in my Vim editor compile with GCC gets this assembly which you expected it to get, right? That's why I wanted you to have good solid foundation of assembly. I might ask you to write a couple of lines of assembly, but kind of by example, so kind of move lines around, but it's coming in one of the homeworks in which you actually will boot into main, right? But that's, again, pay attention. Okay, before starting the assembly, right? So a quick recap of what CPU is doing internally, right? We all know that it does this fetch, decode, execute loop, right? And it's kind of easy, right? So you have two magic registers, instruction pointer, and I mean, it's not written in stone that you need stack. You can compile computations without stack. There is even a C compiler, which compiles a subset of C to run without stack, right? Because there is just no memory, for example. There is only read-only memory early on when BIOS boots, right? So there is no really way to push anything on a stack, right? But normally you will have a stack pointer, right? And we generate an instruction pointer, the CPU reads this instruction from memory into internal registers, which do decode the instruction. Who took my architecture class, people probably know, they understand how it works. There is the step which does register read, which reads values from registers into intermediate latch registers, which then pipe those results into, for example, LEU units, and LEU does the addition, right? For example, because that's an addition operation. If fault occurs, we'll go into exception handling paths, and we'll spend a fair amount of time. Again, we'll take in-depth look on the interrupts and how they work from both devices and how to implement system calls with interrupts, right? But essentially, if no interrupt occurs, then you commit the result of the instruction. If the instruction did not change instruction pointer, you simply go to the next instruction by adding the current value of the instruction pointer with the size of the instruction, right? Because that's how you get to next, and start executing again. So pretty simple, right? And this lecture, which introduces x86 assembly, we will be looking at 32-bit version, is based on this David Evans x86 assembly guide. So there is the link. You can always open it and read a little bit more if you get confused. And it also linked from the class web page, right? Okay, cool. So as I said, we're talking about 32-bit version. They're almost identical. There are some minor changes about introducing IP relative addressing in 64-bit assembly language, which will simplify implementation of something what is called position independent code. And of course, they added registers, right? So now if 32-bit has only 8 general registers, 64 has 16, right? And they're longer, they're 64 bits, right? But I'm pretty sure the step to understand 64-bit assembly from 32-bit is minimal. So it's a baby step. So you will all succeed doing it. I'm teaching 32-bit version because we are using 32-bit version of x86 still, although we can switch in the future at some point. And we have a port, but we somehow, I don't know, didn't switch. Actually, one of the students from this class created the port. And you can take a look. He was in the class in CS 238p. I think last fall, and he was great. I mean, I'm still hoping he will come back. Yeah, so you guys can make a contribution as well. Okay, point. x86 is large and complex, but it has a small core, and this core is relatively easy. So it's not super hard to understand this core. So I'm talking about the core today. The core has 3 main groups of instructions. Ones which implement data movement, so moving essentially values from memory to registers and from registers to memory and between the registers, right? That's easy, essentially move instruction. There are some arithmetic operations which allow you to do addition, subtraction, division, multiplication, bit operations, and stuff like that. And there is a group of instructions which implement control flow, meaning that you can jump, you can call a function, you can return from a function, right? Okay, let's take a look. So first, those 8 general registers, right? So they have a names starting from A, right? So and E stands for 32-bit version of this AX register. AX was 16-bit versions. So that entire thing used to be AX, right? And it had 2 parts, AH high and AL low, 8 bits. 8 bits, this was 16, and now EAX is 32-bit registers, right? And they're given names, but it's just like symbolic names that don't have really any special meaning at this point. EAX, ABX, ECX, EDX, ESI, EDI, those guys don't have lower parts, but that's okay. Stack pointer, which I mentioned, it can be used as a general register, but normally it's occupied by the compiler to maintain the stack. And there is another register which will become clear in the future, which can or may not be maintained by the compiler for a special purpose of maintaining the stack frame. And when we get to the calling conventions, probably next time, I will explain why the stack frames are needed, right? But it can be used as a general register as well. A good question. Where are those registers located relative to the CPU? Who can tell me? I mean, I'm asking some kind of a unit. Yeah, exactly, Sean. Inside the CPU, on the chip. And just to be even more specific, look, if I have this picture of a 5-stage pipeline, which is, of course, it's not Intel Pentium or Intel Skylake, which have like 20 stages, or maybe like up to 30 stages, right? It's only a 5-stage in-order pipeline, but still realistic. It can run on some embedded devices, right? Look, remember I told you there is this LEU which will actually do the addition, right? And there is this intermediate latch register which will hold the value of registers. So register is like a tiny memory of only 8 32-bit values, and they have names, like instead of like 0, 1, 2, 3, they have symbolic names for humans, right? And CPU maintains them a little bit differently, but the idea is that like they're here. So in this first cycle, you can read the registers into the latch, and then in the next cycle from a latch, they go to the input of the LEU. So to access a register, you only need 1 cycle, right? In the next cycle, it will become available, or you can think of it as it's available in the same cycle. Depends on how much you want to reason about the pipeline. And the reason I was asking specifically to clarify that it's not the cache. The cache will be this memory, right? So there will be a data cache, and there will be instruction cache, right? And program counter or instruction pointer will be reading from the instruction cache, and we will be reading and writing into the data cache. And this typically takes like 2 cycles, and this also takes 2 to 3 cycles, right? But CPUs, like because of pipelining, you can conceal those latencies, right? Okay, so back to the assembly, right? So we got where the registers are. In this today and in this lecture, we're going to be using the following notation. So RAG32 is any of these general 32-bit registers. RAG16 is any 16-bit register. RAG8, any 8-bit register. RAG is any register, any of these above, right? Memory is memory, right? A memory address, and this is how we usually refer to a memory address. So if EAX is OX55, so that's essentially the address in memory. So essentially at address OX55, there will be something, right? And that's something might happen. So maybe it will read it from memory, or will write back into this memory as well, right? A constant is a 32-bit constant. So instruction itself in a body of instruction can include the constant. So for example, if you have a 32-bit constant plus some instruction opcode, that immediately brings you up to already like 5 bytes, right? Because this is like 4 bytes. That's why the instruction vary in size, right? So that's magic of x86. Constant 16-bit constant 8, any 8 bits constant, and constant any either 8, 16, or 32 bits, right? Okay, easy. Move instruction. The first instruction which moves data from memory into registers and vice versa, right? And between registers. Okay, let me take a question. If we write into AX, for instance, will H be overwritten? Yes, it will be overwritten. Yeah. So, and if you write into EX, all of it will be overwritten, right? So, but you can change only half of it if you write into AH or like AX, right? Okay, here, it copies the data item referred by its second operand. So those guys are called operands, number 1 and number 2. And we're talking about Intel assembly, not AT&T, because in AT&T it's flipped, right? Intel is a little bit easier to read, arguably, for, I mean, doesn't really matter. So I don't have a strong preference, to be honest. But what happens is that it reads from the second into the first, right? So here, for example, it will read from register pointed by this operand into this register. Here it will read from memory into a register. Here it will read or write, if you like, from register into memory. Here it will read from constant into a register, and here it will write a constant into memory, right? Let's take a look at concrete examples. Here we copy the value which is inside EBX into the EAX register, right? Pretty easy. Here we store 5 into the memory location pointed by the var variable, right? So whatever var, so it's some number here, right? Is, again, our favorite number is 55. This 5 will be written here, right? And it's 1 byte, because we say the size is byte. You can specify the size as a word, then it will be like 4 bytes. So here we would, like, by default is 4 bytes actually. We move the 4 bytes in memory at the address contained by pointed by EBX into EAX. So if EBX is pointing to somewhere here, and there is like 17, for example, that 17 gets moved into the EAX register, right? And vice versa. EBX here is saved into memory pointed by var. Maybe var is pointing here, right? So EBX, which was, I don't know, 57, for example, 57 gets saved here, right? Move 4 bytes at memory address ESI plus 4 or plus minus 4, right? So you can do an arithmetic operation here. So x86 allows you to do that. That's convenient because, you know, if you have data structures which are like has 2 members, each of them is 4 bytes, maybe you like step by 4 or something like that, right? Although one would imagine that you probably would do plus 4, but it just to illustrate that you can use negative numbers as well here. Here, move the contents of CL into the byte at address ESI plus EAX, right? So you can also use 2 registers here as an arguments, and then CL gets moved into like the address, which is the sum of those 2 registers, right? Again, the base of the data structure plus an offset will give you a specific field. That's why maybe this one is a base and this one is an offset, right? Of that specific field. And then you moving, if you have a data structure, this is the base, which is ESI, for example, and this is the offset. You are saving something. Your CL is saved here, right? Got it? Okay, cool. Here's a concrete example how a compiler might generate a code for this data structure, which is an array of pointers or array of points. So each point is a struct with two integer fields. So each of them is 4 bytes, right? X and Y. And you have an array, right? So you have an array of 128 of those guys, right? So a total of 128, and each of them has X and Y, right? So that's one element of the array. For example, i's element, right? So for example, if you want to load a Y coordinate of i's point, so like your C code will look something like that. X is ith element of the array and its Y field, right, into Y. The compiler will generate the code, which will look something like this, right? So we will have EBX is a base address of the points array, so it will be pointing right here. EAX is an I, and each element is 8, right? That's why it's multiplied by 8. And since you're accessing the second field, so this one is 4 bytes, and the second one is 4 bytes, you're doing plus 4, right? And this value, which is sitting here, maybe it's value 7, gets saved into the EDX. So 7 will be here, right? Got this example? Let me stop here, for example, for a second, take questions. On a 64-bit system, will the move instruction move 8 bytes instead of 4? Yes. yeah, you will, but you can always say 4 as well. I think by default, it depends on the assembler, right? So sometimes you have to explicitly say it and think on until it defaults to this. Okay, all good. I'm used to using, instead of for accessing memory allocation. What do you mean? Because you were using AT&T syntax, that's fine. It's just different syntax, and I think there will be, I can send a link to which compares the two syntaxes. And all the two chains which we're using in the class, I think by default, like when you do make an x86, it will generate, because for each compiled program, it will also generate an assembly output, a human readable assembly output, so you can read and like compare. And I think it generates Intel by default. That's why also, but I can be wrong actually. Maybe it generates AT&T. Okay, another instruction, load effective address. So it's most easy to understand the meaning of this instruction through example. Imagine we have the same array of 128 points, right? So this is the array. This is the ice element of this, like with X and Y fields, right? This is ice. And when we use the instruction like that, which moves something like value 7 into the EDX, right? A different instruction, which is called load effective address, you exactly look, it's exactly like this, 8EX plus 4 plus 4. Instead of moving this 7, it will take the address of this 7. So whatever it may be X, maybe the address is 50, hex 55, right? And this X55 will be moved into ESI register. So this is the C code. So essentially this ampersand means take the address of this Y coordinate, right? And use it, like assign it to an integer pointer, right? Got it? So it's the move versus load effective address. Unfortunately, load effective address is also often abused by the compilers because it's a powerful instruction which allows you to like do different things. So let's take a look at a couple of examples. So here we can do an addition with 3 arguments, because normally addition is done with 2 arguments on x86. There is no instruction which does addition with 2. But here we can say EAX, EBX, and a constant, right? 3 arguments. Or you can normally addition, and we'll take a look at it in a second, will override the first operand. But load effective address, like you can say, okay, override EAX instead of EBX, because if you would be doing addition, you will have to write something like add EBX plus like EBX ECX, and that would be equivalent to saying EBX equals to EBX plus ECX, right? But here if you want to use EBX as an argument, you will end up overriding it. But load effective address allows you to preserve this old value and instead use a different register for saving the result, right? So it also has a weird property that it can be used as a multiplication by a restricted set of constant, right? So n can be 2, 3, 4, 5, 8, and 9. Hold on, because n can be 1, 2, 4, and 8, right? And if you think about it, you can multiply by those constants, right? Again, just watch out for it. Don't get scared. So load effective address is not that frequent, but sometimes it happens. Normally as an addition. Now we're moving to the second set of those instructions, arithmetic and logical operations, like pretty easy here, right? So again, addition adds together 2 operands, like operand number 1 and operand number 2, and stores the result into the first operand. So essentially here, operand number 1 gets the value of operand number 1 plus operand number 2, right? Again, kind of intuitive, so we can understand it. So you can use 2 registers, saying like add 1 register and another and put the result back into register. You can use register and memory and a register, saving the result back in memory here, a register and a constant, saving back into register, memory and a constant, saving back into memory here, right? Okay, cool. So a couple of examples here again. So for example, we're adding 10 to EAX. So because we say EAX is the first operand, the result will be placed back into the EAX, right? So here we have something like adding 10 to the constant to a single byte, because we use byte here, stored at the memory address var. So essentially, if var has a value, again, x55, so whatever was there, maybe it has 7. So 7 plus 10 will be 17. So we'll put here back 17, right? So simultaneously like reading the memory and writing it back. It's a little unusual, but x86 allows you to do that. Sub is an integer subtraction. Store, it's the value of its first operand in the value of its first operand, the result of subtracting the value of its second operand from the value of its first operand. So again, by example, it's a little bit easy. So AL will get the value of AL minus AH, right? So here we're subtracting 216 from EAX and putting the result back into EAX. That's why we subtracted 216, right? Increment and decrement, so kind of intuitive as well. So you say increment something by 1, decrement something by 1. So here subtract 1 from the content of EAX, increment the value in memory at location var, right? Okay, got it. So bitwise separations like AND and XOR, right? So what happens here is this: if you rewrite as binary, so it's all zeros, but the last 4, since it's F, will be 1s, right? And if you ending with, no matter what you have here, like maybe there was 0, 1, 1, 0, 1, 0, 1, 0, since you ending anything with 0, the result will always be 0, right? That's why these bits are cleared, and those are preserved because 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 1, and 0 and 1 is 0, right? So those 3, 4 are preserved, but everything else is cleared, right? So that's bit end. XOR, essentially, that's a quick way to set EDX to 0, right? Because 1 and 1 XOR equals 0, and 0 and 0 always equals 0 as well. And you always XORing with itself, right? Shift left, shift right. So essentially shift the value by the number of bits, right? And it's equivalent to multiplication and division by powers of 2, right? So it's a fast way to implement multiplication and division by the powers of 2. Of course, you have to handle overflows, right? So you have to be careful with this. But overall, you probably understand the idea. Integer multiplication, so multiply the contents of EAX by the 32-bit contents of the memory location var, right? And store result back in EAX. Or for example, another example here, multiply EDI by 25 and put it back and put it into ESI, right? So there is this unusual form as well. There is a division operation I don't even cover, but you can read how it works. And there is the bitwise NOT, flips all bits from 0 to 1, 1 to 0. Negation takes a value and like gives you a negative value, right? So kind of you can see that, okay, this is enough to do basic arithmetic operations, unless you like want to do floating points. You say, look, I kind of got it. Like if I want to do my hash table and like I know how to do offsets with data within data structures, I even can implement a hash function as long as it's all integer, right? Which is typical case, like some shift to the left, shift to the right, might be multiplication by magic constant, right? So in division sometimes. So that's enough to build like powerful programs. What we're still missing here is the ability to implement conditional statements and loops, right? Because we didn't cover them. And those will be implemented with control flow instructions, with jumps, with non-conditional and conditional jumps. Again, remember, if the instruction doesn't change the instruction pointer, you just move to the next instruction. But some instructions override instruction pointer, right? And then you jump, right? Then instruction pointer starts pointing to somewhere else in memory, somewhere here, right? You jump and the CPU will start again, like we'll be doing the same fetch, decode, execute loop, but instruction pointer will be pointing to this instruction that will continue running here, right? And maybe you will jump back, or maybe if it's a loop, or maybe you will jump somewhere else, right? But that's what jumps do, right? Okay, let's take again, like a closer look here. Instruction pointer is this 32-bit value indicating the location in memory where the current instruction starts, right? So essentially memory address of the current instruction which we execute. And you cannot change EAP directly. So you can't really do, if you can do something like move into EAX from EDX, for example. So you can't really do move into instruction EAP pointer, right? EDX. So this is not allowed, right? So, but you can jump. So you can essentially jump to EDX, and then essentially EAP will be assigned that value, right? Okay, let's take a look. So first, notion of labels, right? So there's a human readable locations in the program. So and with this column here, and here it's a begin label. You can put it anywhere, and assembler will be, if you use this later label, the assembler and the linker will work together to make sure that the jump lands on specifically on this instruction, which is under the label, right? The first instruction which we cover is a non-conditional jump. So it always jumps, right? So here, for example, jump to a label, right? So here we have a begin label and we just jump to it. So this, instead of executing this next instruction after begin, we will always jump here. It looks like an infinite loop, and it does, but maybe there is a conditional jump which jumps outside here, right? So for example, why do you need non-conditional jumps? So for example, in combine, if you want to do if some condition, then part and then else part. The compiler can compile it. You can do some CMP, some kind of check for condition. You can do a conditional jump when equal, which we'll cover on the next slide. And it might jump to maybe like an else part of the if then else block, right? This is an else part. But imagine you didn't jump, the condition was not equal, you start executing the if part, right? So this is, or then part. At the end of this, right, you clearly don't want to execute else as well, right? So here you will be jumping and you will jump outside of else, right? So to skip those instructions and don't execute them twice, right? So that's why you need both conditional and non-conditional jumps, right? Okay, so jump jumps only when the condition is true. And on x86, those conditions are saved in a special register, which is called eFlags or flags register. So it's a 32-bit version of a flags register, right? And so, for example, eFlags stores information about the last arithmetic operation, right? It can be addition, can be subtraction, can be explicit comparison, right? And there are different bits. And for example, bit number 6 indicates if the last result was 0. Bit number 7 indicates if the last result was negative, right? And then based on those bits in this register, and I never mentioned eFlags registers, but it's yet a separate register, and you can't really affect it. You can't move into it. You can save it and restore it, and while restoring, you can always overwrite flags, right? If you want, but normally people don't do this. It jumps based on those flags, right? So let me take you an example, give you an example. So here we jump if flags indicate that something was equal. You can jump if it was not equal, jump not equal, right? Jump when it was a 0, jump when it was greater, jump when it was greater or equal, jump when it was less, or jump when it was less or equal. Got it. Okay, so I probably just got kicked out of the meeting, and you probably don't see my screen anymore. Is that correct? Let me just re-enable sharing.
Yeah.
Yeah, let me do the sharing again. Thank you, Zoom, for failing me. But maybe it's a weird combination of Linux and Zoom. No one really optimizes Zoom for Linux. That's the problem. Okay, let me quickly share. Come on, let me share. No, not this one, this one. Okay, back to the lecture. So can you see my screen now again? Say yes or say no. Don't even see the chart. Where's my chart?
Yes.
Yes,
we do see.
Yeah, sorry. Yeah, something went wrong. Okay, disconnected. Hopefully not going to happen again. So chat is here. Yes, no. This nonsensical thing is here. Okay, so otherwise you will start executing. If it's less than equal, you will jump to somewhere to the done label. If not, you will continue executing this instruction after it, right? So, and what is this compare instruction? So compare essentially compares the values of the two specified operands. Like it can be a register and register, register and memory, memory and register, or register and a constant, right? And sets the conditions in the eFlag register, right? So it's kind of equivalent to the sub instruction subtraction. And this is how it's probably implemented internally, except that the result of the subtraction is discarded. So it's like you don't have to overwrite a register. Like if it's a CMP, EAX, and EDX, neither of these will get overridden. Whether if you will do sub, it will set the same flags registers, right? But you will lose the value in EAX, right? Because this comparison will, like the subtraction will go through, and the result will be placed back in the EAX, right? So here is an example. So you're comparing a 4-byte stored at location var with 10, and if it's equal, then you jump to the loop label, right? That's how you can, for example, implement a loop, right? So you will be you're not going to jump, or like compilers can compile loops differently, right? But essentially you can say, look, this is a body of a loop. Depends, like you can say compare with 10, I runs from 0 to 10, and on 10, instead of like your next instruction here would be like jump to begin, which would be somewhere over here. But if you reach 10, then you jump. If you jump equal, you maybe leave the loop, for example, right? A little unusual, but maybe that's the way to compile. That's one way to compile, but you can, like, we'll take a look at the actual compiled loops later on, but you will see how it works, right? Okay, cool. So any questions here? Let me stop for a second. I was going a little fast, just to make sure that we finish this part of this lecture. All good? Yeah, it was relatively simple, I agree. And this is where it gets a little bit non-trivial. So stack and procedure calls. And actually, it probably makes sense to start next time, just because it's a solid piece of information which I want you to understand from top to bottom. And yeah, so let me just, we have 3 more minutes. I can hang out here taking questions. So go ahead, ask them.
Do you want to go back to the previous slide you were?
Yeah, which one?
Oh no, I just wanted to see it again for the next 3 minutes. Thanks.
What happens when you add or any other arithmetic operation a number larger than 32 bits? Example add. Yeah, it's an overflow. So there will be an overflow flag set, and essentially it kind of like the bits which will overflow will be just lost. You will have a single E flag saying that, okay, overflow happened, and that's it. Those will be set correct, I think. So you have to be careful with that. And in C, overflow is what? Undefined behavior, I think. There is really no answer. Some languages don't overflow, like Rust, I think. It doesn't. It will panic at this point, saying, okay, what else? Do you understand how if then else will be compiled, right? So we talked about it a second ago. So if else, so it will be 2 parts with a couple of jumps in between them, right? That's important to understand. Like C has this transparency, meaning that you will be surprised. Like we'll take a look at real C programs, and I mean, optimizations change stuff, but complicated code still, like, they only like help you to understand it better. But really, it's really what you would write as a human. That's what compiler generates, right? So you will quickly understand what assembly is doing. Okay, if there are no questions, let me stop here, and then next time we will start with stack and procedure calls, and we'll probably finish them, and we will start a new topic after that, which will be calling conventions. So essentially connected to this, essentially how you invoke functions and how you will pass arguments between the caller and the callee. So, okay, thank you, and see you on Wednesday then.
Hello.
Yep.
I have a question about computer system architecture. Can I ask now?
Yeah, go ahead.
Yeah, so like I'm currently enrolled in some heavy subjects, so I'm planning to drop one and take a little more, like less heavy subject. So I was thinking if computer